Okay, we're going to work pathways problem 6.15. This reads at constant temperature, a sample of helium gas will expand from 922 millimeters to 1.14 liters against a pressure of 2.33 atmospheres. We want to know what work in joules units was done by the gas. Okay, so let's set this up with a visual depiction of what's going on. We've got to think about having a container of gas that's almost like a closed-off syringe, okay? The helium gas is inside this container, and there's a little piston at the top, okay? Now, the original volume of the helium gas is stated in the problem to be 922 milliliters. It's a little less than a liter. If I do the conversion right off the bat here, I have to divide by 1,000. It's 0.922 liters, okay? So hopefully that's pretty straightforward for you right now. That's our original volume. Now what we're going to do is we're going to allow this gas to expand in volume basically and push this piston up. Now that doesn't come free. We have to do work. But the thing is that once the volume expands, the final volume will be larger at 1.14 liters. Now, as I mentioned, this piston doesn't move freely. It has to push against it. Now, what is it pushing against? Well, it's pushing, in this case, against a pressure of 2.33 atmospheres. So we're going to say that this gas is going to do work on the surroundings. It's going to push this piston, exert a force, and thereby doing work on the surroundings. And this whole problem then is about calculating how much work, what is the quantity of work done by the gas, okay? So this type of work in chemistry circles here is called PV work, for pressure volume work, okay? And it just so happens that there's a very convenient formula for figuring this out. The work, W, is equal to negative P times delta V, hence PV, right? Pressure and volume are what's the key variables here. Now it's just volume, right? Remember when we saw this triangle, that denotes change in chemistry. So we're looking at the change in volume that occurs for a gas, multiplied times P, the pressure that gas has to work against or push against, okay? So it's a pretty straightforward equation. So work is equal to negative P, where P is the pressure. In this case, that's 2.33 atmospheres. And I have to multiply that by my delta V term. When you're computing delta quantities, or changes in anything, okay? What I want you to get used to doing is writing that delta V like this. When you're computing the change in volume or change in whatever, okay, it's always the final measurement minus the initial. Always final minus initial, final minus initial. Doesn't matter if we're talking about volumes, pressures, whatever it is we're talking about. If it's delta something, it's final quantity minus the initial. This is pretty useful for you, okay? Because instead of getting confused about well, which one comes first, is this negative, is this positive, if you remember the final minus initial, it becomes pretty easy, okay? Because all we need to do is take the final volume in this case, which is 1.14 liters, we're given that in the problem, subtract the initial in liters, which is 0.922, these are both in the liters, remember we converted over here, all right? Find that difference, multiply it by 2.33 atmospheres, and I'm in business. Remember, these are both in liters, okay? So if we do the multiplication and we work this out, W equals negative 0.508. And what units are going to come along for the ride? It looks like it's going to be what? Atmosphere dot liters, or atmospheres times liters? So negative 0.508 atmosphere liters. That was the work that's done, the PV work. Now here's the thing. They ask us in the problem to compute the work in joules, not in atmosphere liters. So we have a little bit more work to do. But fortunately, this is not so bad, okay? Because in the problem, if you read it carefully in your book, they give us a conversion factor. I'm going to write that up here on the board. The conversion factor is that 101.3 joules is equal to 1 ATM liter. This makes our life a lot easier now that we've got this so armed with this, because all I need to do is take my 0.508 ATM liters and convert to joules using the conversion factor. And I've been told that 101.3 joules is equal to 1 ATM liter. If I do the conversion, I end up getting negative 51.45 joules on my calculator. If I look back to the beginning of this problem, it seems like 3 sig figs is probably a pretty good place to kind of call it quits. So I might, in this particular case, just round up to 51.5. I usually just round up at the last digits of 5, okay? So 51.5 joules of work energy was required to cause this expansion against 2.33 atmospheres, okay? Now notice it's negative here. Remember the sign conventions. That's important for this chapter. Very, very important in chapter 6. Does that negative sign make sense based on how we define negatives and positives for energy flows into and out of our system and into the surroundings, okay? Remember, if work is done by the system, we should have a negative sign associated with that. But if work is done on the system, if I was to compress this, say, then that would be a positive sign. Okay, so the fact that we have a negative sign here, and our answer makes perfect sense because in this particular case, the work is being done by the system on the surroundings. Now, in the mathematics, where does that really show up? Okay, and I keep coming back to this point right here. Remember I said final minus initial, final minus initial? It's always defined that way for delta. It changes, okay? This is the key part of the mathematics for assigning the sign ultimately on the result. If this works out to be a positive number, like it was in this particular case, if the gas expands, then you can see that the answer will be negative by virtue of the negative in the equation. However, if the gas contracts and this ends up being negative, then we have two negatives, we multiply together, the answer becomes positive. Okay? So this is a nice little example problem. It's pretty simple, the mathematics. But again, it allows you to familiarize yourself with what's going on, this idea of PV work, and how to compute changes in variables, and the sign convention, whether it should be positive or negative. All this is important stuff.